So let's start with an example for this tangential component of the acceleration and the normal component of the acceleration. So let's say your position function is given as 2t and then 4 over 3 t to the 3 over 2 and then 1/2 t squared. We played with this function before when we did the example of unit tangent vector. The question I would like to solve is first find t of t, which I'm going to be a little brief because we already did this in previous notes. So if you look at your previous notes, you probably have this. But b, what I really want to do is the tangential and the normal component of the acceleration. Okay? All right, solution. How do you find the, oh, I need this hat here. What does this hat mean? It's a unit vector, okay? So this thing called unit tangent vector is obtained from the velocity vector by making it into a unit vector, by normalizing it, right? That's because velocity vectors are always tangential to the trajectory. Okay? Now, this is the derivative of this, which is 2. And then when you differentiate this, 3 over 2 comes down, canceling with 4 over 3 to give you 2. And subtracting 1 off 3 over 2 gives you 1/2 power. And then 2 comes down, canceling the 1/2, giving you t. And square root of these things squared. So square of 2 is 4. Square of 2 is 4. Square of t to the 1/2 power is just t. And the square of t is t squared, and you're supposed to add them all. That's how you find the norm, right? Okay. And that gives you 2 square root of t. You can rewrite t to the 1/2 power as square root of t. And by the way, that's why I got t when I squared it. Okay. And then t. And then this thing actually can be factored. If you factor this, think about two numbers that multiply to 4 and add to 4. Right? This is t squared plus 4t plus 4. Two numbers that add to 4 and multiply to 4 is 2 and 2. Right? So it can be factored as t plus 2 squared. It's t plus 2 times t plus 2, so it's t plus 2 squared. And therefore, when you take the square root, it just becomes t plus 2. Okay, so that's your t of t. That's the answer to the first part. Now let's think about part B. I did this rather briefly because we've done this before. Okay, let's think about part B. So to find the tangential and normal part, you first need to find the acceleration. How do you find the acceleration? Take the derivative of v, right? Yeah. So that's how you first find acceleration. Okay. In our case, it's 0. When you differentiate this, 1/2 comes down, canceling the 2. 2 times 1/2 is just 1. And then you get t to the negative 1/2 power. Okay. Because you subtract 1 off 1/2, it's negative 1/2, right? And if you differentiate t, it's 1. Therefore, this is same as 0, 1 over square root of t, comma 1. And that's because negative means it's 1 over, and 1/2 power is square root. Okay, so that's your acceleration. Now, what does this have anything to do with AT and AN? Well, the relation is that if you have acceleration, it can be divided into two parts. One is the tangential component, which is in the direction of t, and the other is the normal component, which is in the direction of n. The picture for this is you have trajectory, and the t direction is here, and n direction is here. And if you have some kind of acceleration at this part, if this is your acceleration, it has this AT component, and this is your AN component. Now, because the principal unit normal vector always points to the way that the curve is bending, it's always in this same, in the direction where you have the force acting. So if you have something moving and it's bending this way, that means there's a force pulling it to this side, right? And what that means is that AN tells us how much it's bending. If you have a lot of AN, that if you have huge AN, that means there's huge force, because F is equal to MA. F equal to MA means that force is large if acceleration is large, right? And another thing is that the direction of the bending is always given by the principal unit normal vector. And therefore, AN should always be positive. Okay? So, I want you to think about the meaning of AN. Right? Quick turn means AN is big, okay? And also that AN is always positive because it's always the direction of n, it's bending. I mean, if you have this picture, you can't have any acceleration going that way. That doesn't make sense. If acceleration is going that way, it should be bending that way, right? If acceleration is that way, then if you project it to n, the AN will be this much, which is negative, right? But that never happens. That's what I'm trying to say. AN has to be always positive. However, AT can be negative or positive. There's no restriction for AT. What would AT being negative mean? What kind of meaning does it have?
Slowing down.
It's slowing down. Okay. If AT is positive, then it means it's speeding up. If AT is 0, even if AN is non-zero, if AT is 0, that means the speed is constant. Okay, so it's only changing its direction if AN is positive, and if AT is 0. Okay. All right, so that's the physical intuition that you should have when you see this thing, that A is equal to ATT plus ANN. Okay. Now, let's think about how we can get AT from A. Well, one possible method is the following. A dotted with T, let's think about this, would be AT T plus AN and dotted with T. And then if you distribute, you have AT T hat dotted with T hat plus AN and dotted with T hat. Okay. How do you do the dot product? Well, if you're given component form, it's easy to calculate, but if you're not given the components, you're supposed to take the norm of the first, norm of the second, which is same as the first in this case, and cosine of the angle between. What's the angle between T and T?
0.
0. So this is 1, right? So you end up with you end up with ATT hat squared. Okay. Now what about this? What's the angle between these two? N and T. In that case, what's the dot product? Dot product is? 0. Okay. Every time you have dot product of two vectors which is perpendicular to each other, then you have 0. You should actually know these things by now. Okay. Whenever you have dot product among perpendicular vectors is 0. Whenever you have a vector dotted with itself, it's its norm squared. Okay. That's something that appears frequently, so you should memorize that. Okay. All right. Now, what's the norm of the t vector? What does this hat mean? Unit vector. So what's the norm of the t vector? Huh? 1. Unit vector means the length is 1. So this is 1, so you get AT. All right, so we have a very good formula here. The formula is that A dotted with T is AT. So you can use this formula to figure out your AT. Now, what about AN? Well, you can do the same thing for AN. You can take A dotted with N, and the same kind of logic says that this will be 0 if you dot it with N instead, and N dot N will be 1, and it leaves you with AN. However, for practical calculation, that's actually not a good idea. The reason for that is you have to have the n vector to do that, and n vector is notoriously hard to calculate, right? We tried to do the n vector even for a specific value for this, and it wasn't an easy calculation. So because of that, usually you don't want to do it that way. Instead, what you do is, in this picture, if you look at it, this is AN, that's AT. This is AT, so that's AT, and that's AN, and this is 90 degrees. So there's a Pythagorean theorem acting on it. Okay, so what's the Pythagorean theorem? Pythagorean theorem for that is that if you have AN and AT, square, sum it up, that's same as the length of A squared. In other words, if you solve this for AN, you have AN equals the square root of the norm of A squared minus AT squared. So that's the more reasonable formula to use when you have to find AN. So let's actually do the calculation with these two. Right? The first thing is you have AT equals to this 0, 1 over square root of t, comma 1, dotted with this vector 2 square root of t, comma t, divided by t plus 2. Which is, when you're given in coordinate form, you have to multiply the corresponding coordinates and add them, right? So if I multiply 0 to 2, it's 0. If I multiply 1 over radical t to 2 radical t, they cancel, giving you 2. And then 1 times t is the third one. And t plus 2 is divided there, so I just divide afterwards. See, this calculation that with the scalar multiplication is actually associative. So whether you do this divided by the scalar and then multiply this, or whether you do this dotted with this and then divide the resulting by t plus 2, it doesn't matter. Okay, so you get the same answer. And at the end of the day, you have 2 plus t on top, 2 plus t on the bottom, and you get 1. Okay. So amazingly, usually because because this is a function of time, acceleration is function of time, therefore usually the tangential component and the normal component of the acceleration ends up being function of time. But surprisingly, in our case, this at came to be a constant. Okay? But don't expect that to be constant always. It will usually change with respect to time. And then, what is your an? An is square root of length of a squared minus at squared, which is, let's see, length of a is this one. This is the length of a. Length of a is 0 squared plus 1 over square root of t squared plus 1 squared. That's the length of a, right? And then you have to square it, and then subtract at. But at we just found out to be 1. That's what we have. Okay, and then these cancel, and then 1 minus 1 is 0, so you end up with just 1 over square root of t. Yes?
Why is there 2 square roots?
No, how do you calculate the
okay.
norm of a? You need the square root, right? Yeah. And then the formula itself has a square root. Do you have any other questions on this calculation? I just took the norm of this, which is square root of square, 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 add them up, right? Placed it in here, and then inside this formula there's a square in here, square there, so that's what I did. And then after getting rid of this square root by this square, you see that 1 square minus 1 square, that cancels away, and you just end up with, well, let me just write down that. After canceling, this is what you get, and then canceling 2 and the square root, you have 1 over square root. Lots of square roots. I see actually 3 of them here. Okay, so that's your normal component of the acceleration, which means that it's bending. Now let's think about what this is saying. As time goes by, is it bending more or less? Less. Okay, so it looks like when time goes to infinity, it bends smaller. That's something that you can read off from here. Okay. All right. Now let me tell you another way to look at this problem. What is the velocity? Now, what is the speed? Speed is the magnitude of the velocity, right? Let's see what that is. It's this one, right? Magnitude of the velocity is this one. We already have it calculated, which we simplified it to be t plus 2, right? So that's the speed. Now, can you see what the acceleration, tangential component of the acceleration is just by looking at this? 1. Why? Because if you differentiate it, it's 1. So you can see that the tangential component of the acceleration is actually the derivative of the norm by time. So you actually have 2 different formulas for ATs. You may find AT if you already have your unit tangent vector with you, then you can find your AT by doing this. Or if you don't have it, then maybe this is quicker. So that's the well, we already have the answer to this, but let me finish this section by actually proving that that's true. Okay. Why is the tangential component of the acceleration same as the derivative of the speed? here's a quick proof. Now, if you have velocity vector dotted with itself, what do you get? If you have any vector dotted with itself, it's same as norm squared, right? It's magnitude squared, okay? And this is perfect because on the left side you have the velocity, on the right side you have the speed. Okay? Now we're going to differentiate both sides by t, where this really means d dt, okay? Okay, on this left side, I told you that dot products also obey the product rule, right? So I can apply the product rule and say Vt prime dotted with Vt plus Vt dotted with Vt prime is what you get on the left side. Okay? On the right side, this is a nested function. The speed is nested inside the square function. So I can use the chain rule for this. So the chain rule says 2 comes down, and then times the inside function. And the inside function has to be pulled out and differentiated. So I have to differentiate. This thing. Okay? All right? Okay, now let's see. What is this? If you take v and differentiate it. Acceleration, right? That's also acceleration. And dot products commute, so I can switch them around, right? And you end up having the same thing, so you double it. So you have twice of acceleration t dotted with v of t equals to twice of v of t. And let me rewrite this as d vt because that prime means you're differentiating by t. Now cancel the 2's and then divide this over to the other side. Let's see what you get. What's this? The unit tangent vector, right? This is a unit tangent vector. But didn't we just prove that AN is same and AT is same as this?
Yeah.
I just proved. I raised it here, but I proved it, right? AT is same as that. Therefore, this calculation shows that AT is same as the derivative of the speed. And that's another good way to see that the tangential component keeps track of the change of the speed. If AT is positive, that means speed is increasing. If AT is negative, that means the speed is decreasing. Okay? And that's it. So you probably, to summarize the formula that you need to know, so let me put a summary here. AT has 2 formulas. You get to pick and choose which one's more convenient for you. It's either A dotted with T, or it's the norm of the speed differentiated by T. Okay? And for AN, although it is true that it's A dot N, I don't even want to write it because it's useless in practice. So please try to use the formula. Squared minus AT squared. So these are the 2 formulas that you have to memorize when you find the tangential component and the normal component of the acceleration.